for 3 periods because I have to attend the graduation ceremony this afternoon. So perhaps we study just 1 period and then we will stop the class, all right? And we will continue the class meeting next week on Tuesday, all right? Okay. This all right? Okay. Okay, now I'm going to share the spreadsheet with you. The projects actually you can find the data set on BK Learning, and I suggest you to find your data set and you work on that data set. Okay, and if you have any problem with that, please feel free to ask me. I'm going to upload some more data set if you need them. Okay. No, just pick one data set, or you can. But I recommend you to find your data set, and to get bonus score. If you get your data set and you work on that, and you will get the bonus score. The deadline for the project will be I think I already mentioned that. The deadline will be May let me check. It should be May midnight of May May 13. So you need to submit it before May 14. All right. So you should have about 3 weeks to do it. All right. Is that clear? Is that okay, everybody? Okay, so now I'm going to, last time I would think I already talked about the ANOVA. Today I will talk about the linear regression model, all right? So when we consider a linear a regression model, this is today we talk about regression model. Okay. Okay, so what is that? What is that about? You can think about the a function y equals f of x and y, xz, right? And so in this case, if f is a linear function, you call it a linear model. If f is a nonlinear function, you call it a linear regression model. Okay. If the function f has only one variable, you call it the simple regression model. If it has many variables here, then you call it a multiple regression model. All right. Today, I will talk about a simple linear regression model. So that is the simplest model. Okay. Oh, last time, did I talk about multiple comparison? I'm sure that we haven't studied multiple comparison model. I'm sure. Let me check. This is what we studied last time, right? Oh, I see. We haven't learned. We haven't learned the multiple comparison. All right. So I will talk about that a little bit to finish this one. Can you see it? Can you see it? So last time I think we already studied the how to construct a confidence interval for the mean value, right? So it is mu I equals xi bar plus or minus the t value times the standard error, and the standard error is simply the square root of the variance of the xi bar, and that is the mean square for error divided by the number of observations. So you come up with this one, right? And then you get the you get this result. That is what we'll study last time. Okay. How about the difference in means? Suppose that you want to consider the difference between mu I and mu k. Then you can think of the xi bar minus xk bar, all right, plus or minus the t value times the standard error. In this case, the standard error is the square root of the variance of the xi bar minus the xk bar. Okay. And the variance of the difference xi bar minus the xk bar equals the variance of xi bar plus the variance of xk bar, right? And if you remember, this variance is simply sigma squared. No, I'm sorry. Yes, we should say sigma squared over the ni plus the sigma squared over the nk, right? Where ni and nk are the number of observations in each group, in the groups. And you can approximate sigma squared by the MSE, right? So you get the MSE times 1 over ni plus 1 over nk, correct? You can approximate this by this one. So I can say that the standard error is simply the square root of the MSE times 1 over ni plus 1 over nk, correct? So I can come up with the confidence interval. You get mu I minus mu k equal xi bar minus xk bar plus or minus t value times that square root. Okay. That's why you get you get this result. The error, this error is called the MSD. Okay. So you see that you get the difference in means in the sample means plus or minus the MSD. In our problem, the NK, NI, and NK are the same. They are all 6. So we can get the MSD very easily, which is T times the square root. And you get 2.086 times the square root of MSE times 1 over 6 plus 1 over 6, and you get 3.07. Do you understand? Okay. All right. So you know that mi minus mk equals xi minus xk bar plus or minus the LSD, which is 3.07. Do you understand? Okay. Okay. Now you have a look at let's say mu2 minus mu1. Mu2 minus mu1 is simply the x2 minus x1 bar, right? Plus or minus 3.07. The first term, x2 minus x1, is 15.67 minus 10. So you get 5.67 plus or minus 3.07. This value is always positive, am I right? Okay. Therefore, we can say that mu2 is always greater than mu1. All right. You can repeat what we just did for the other pairs. So you can see that mu3 mu4 minus mu3, that is x4 bar minus x3 bar plus or minus the same value 3.07. And this difference is, what is that? 21.17 minus 17, and that is 4.17. So you get 4.17 plus or minus 3.07. That is positive again. So I believe that mu4 is greater than mu3. Okay. Finally, you can compare mu2 and mu3. Mu3 minus mu2 equal x3 minus x2 bar plus or minus 3.07. The difference between them is less than 3.07, right? You get 17 minus 15.67. That would be, what is that? I think it is 1.33. So you get 1.33 plus or minus 3.07. This one could be, it is the interval that contains the value 0. Okay, minus plus. So 0 belongs to this one, and you can see that the difference might be equals to 0. Therefore, mu2 and mu3 could be the same. So in conclusion, I can say that mu1 is less than mu2. They could be it could be the same as mu3, and mu3 is less than mu4. So this is the result of the multiple comparison. Do you understand? Do you understand what I said? Is it clear? Okay, may I move on? This is actually the result that I just mentioned. Okay, you can compare 4 and 1, 4 and 2, 4 and 3, 3 and 1, 3 and 2, 2 and 1, to see that only in this case, the difference is less than 3.07. So we can think that they might be the same. For the other cases, you always get greater values, so they are different. Okay. Is that all clear? May I move on? So for this problem, we consider only one factor, right? We only have one factor. What if you have more than some other factors? You can consider the following design, the randomized completed block design. An experiment was performed to determine the effect of 4 different chemicals on the strength of a fabric. These chemicals are used as part of the permanent brass finishing process. 5 fabric samples were selected, and an activity was run by testing each chemical type one is random order on each fabric sample. The data are showed in the following table. We will test for differences in means using an ANOVA with alpha equals 1%. So you see that in this case, the chemical time is a factor, right? And all the values here are the response. So the response in this case is the strength of a fabric, all right? But we do have another factor that we don't really we don't want to study it, but we have to, right? That is the favorite sample, and you call it a block. Okay. This one, a block, is used to control the effect of an expected factor, and you call it a confounding variable. So a block can be used to take care of a confounding variable, like the favorite example. Why is that? Because the response, the strength of a fabric depends not only on the factor of chemical type, but also on the block fabric sample. So you need to consider the effect of not only the factor, but also the fabric sample on the response, the strength of a fabric. Okay? So in this case, there are two factors, basically. Okay? So you need to consider a design with two factors. That's the point. Okay. Um, all right. So I think that is the what you need to study in the chapter of ANOVA, right? And now I will move a little bit to the next chapter, linear regression model. All right. Is that clear, everybody? Is this all right, everybody? Is this okay? Now let's consider the following example. The Hooke's law states that the force applied to the spring is proportional to the distance that the spring is stretched. Therefore, you have the equation F equal K times X, where F is the force applied and X is the distance. The constant K is called the spring constant. Okay? And then you can apply the forces of 2, 5, 8, and 7 pounds, which have the effect of stretching the spring 5, 8, and 10 inches. Okay? Then you get the equations 5k equals 2, 8k equals 5, 10k equals 7. Then you get the values of k, 0 0.4, 0 0.625, and 0 0.7. Do you understand? Is that okay, everybody? It is okay. Okay. Um, so from the three values, you can come up with the average value of the three values to get an approximation of the spring constant. So you can find the sum and divide that sum by 3 to get this one. Okay. It is a good approximation. Not really. Not really. Why is that? In order to know if it is a good approximation or not, you may want to know how to measure the error. Okay. Is this all right? Okay, so you consider this data set with 3 points, 5, 2, 8, 5, 10, 7. Okay, and they are the blue, the red dots. So there are 3 red dots here. And suppose that you can find the model, the equation y equals k times x. Okay, and if this equation is true, then you come up with the green one, the green dots. So the green dots are the values, are the points that you use to predict. Okay, is they are what you predict. Okay, they are what you think. You should measure. However, you don't get them. You get the observed values, right? You get the observed value yi instead of yi hat. Make sense? Yi hat is what you expect to observe, is what you predict, and yi is what you actually observed, all right? And then you can compute the difference between them to get ei. Then ei is the error, right? The difference between the observed value and the predicted value, and you call it the residual. Okay, so ei is the residual, which is yi minus yi hat. Okay, and you want these ei to be small. You want them to be small, right? So I find the sum of all those ei. So you get the sum of ei squared, and you get the sum of yi minus yi hat all squared. And then in this model, yi hat is simply k times xi, and you get the sum of yi minus kxi all squared, and you get the function f of k. Do you understand? Y f of k, in this expression, you have only one unknown parameter k, xi and yi are given. So you don't know the value of k, and you want to find k such that the error is small. It means that you want to find k which that minimize the function f of k. So I want to minimize the function f of k. Do you understand? Is that clear? Is that all clear? Is this okay? Okay. So you have a function of one variable as a single variable, and you want to minimize that function. So it is very natural to differentiate the function with respect to k, and you let it be 0, right? So you need to differentiate the function with respect to the unknown parameter, and then you get the sum of 2 times xi times yi minus k times xi, right? And then you get the sum 2 minus xi yi, and then minus and then plus k times the sum minus 2 times xi squared. Okay, and you let it be 0, you should be able, and then you can get the value of k. K is simply the sum of xi yi over the sum of xi squared. Do you understand? Is that all clear, everybody? That's all right. Okay. And then you can have a look at the one that we learned, the one that we have here. So we can compute the value of k like this. You get 0.4. You get 5.2 plus 8.5, 8 times 5 plus 10 times 7, all divided by the sum of the square. And you get this one, right? You can rewrite 5 times 2 by 5 squared times 0.4, right? So 5 times 2 is simply 5 times 5 times 2 over 4 over 5, and this becomes 0.4, right? And then you can get 25 over 189 times 0.4, and so on. So if you compare this sum and that sum, you see that you still have the average values of those approximations, right? 0.4, 0.625, and 0.7. But for the optimal value, you get different weights, not the same weights in the first case. Do you understand? Is that all clear, everybody? Is this all right? So you may see that this is just one example. A function y depends on one single variable. In many problems in engineering and science involve, then you can find the relations between two or more variables. Then you can come up with the concept of regression model, right? Or let's say regression analysis. Another example is that in a chemical process, the yield of the product is related to the process operating temperature. So the regression analysis can help you to build a model that predicts the yield at a given temperature level. In this case, you have just another single variable, but in reality, there could be many variables involved. Okay. And as I said, in this course, we mainly focus on the simple linear regression model. For the project, I suggest you to use multiple regression model. Do not use simple linear regression model, because that is too simple for a project. But for the exam, then you only need to study simple linear regression model. The simple linear regression model considers a single regressor or predictor X and a dependent or response variable Y. So you come up with the model Y equals alpha plus beta X, and you need to estimate the values of alpha and beta. Okay. You can come up with Y equals 2 X plus 5, right? And then you can say, well, you can measure at the points X equals 0, 1 or 2, and then you can get the values. You expect to get the value Y of 5, 7, and 9. However, in reality, you don't expect to get these exact values like this. You may get something like 4.9 for Y, and then 6.9 for Y, and then you get 9.1, something like that. So you come up with like 5 minus 0.1, 7 minus 0.1, or let's say 9 plus 0.1. And then you come up with the model Y equals alpha plus beta X plus epsilon, where epsilon is the random error over here. Okay, so at the point xi, y, x2, xn, then you get the model yi equals alpha plus beta xi plus epsilon I. Okay, you may ask a question about the assumption of epsilon I. Do we have any assumption on that? Epsilon I is the random error, so you may want to know the distribution of epsilon I, and yes, we do have some assumption on that. Epsilon I follows a normal distribution with the mean 0, and the variance is sigma squared. Okay, is that all clear, everybody? If that's all clear, may I move on? Okay. Okay, and what we want to do next is to approximate alpha by A, to approximate beta by B. Okay, and then we want to construct, and also we want to approximate sigma squared by S squared, and then we want to construct a confidence interval for alpha and beta. That is what we want to do. And then again, we may have the model x, y, xi, and yi like that. Okay, and then you can get the yi hat, which is a plus b bxi, and then ei is yi minus yi hat. So you can find the sum of ai squared, that is the sum of yi minus yi hat all squared, and that is the sum of yi minus a plus bxi all squared. Okay, this is the error, right? And you see that this expression has has two variables involved, right? A and B. X and yi are given. The two variables that you don't know are A and B. So I will denote by f of A and B. Okay, is that clear? So you get f of A and B, and then you can differentiate that f with respect to A, and you let it be 0, right? That derivative is the sum of minus 2 times yi minus a plus bxi, and fb is the sum minus 2 xi times yi minus a plus bxi. And you let them be 0, right? From here, from these two equations, you can get the value of a and b. Okay. Besides, you should notice that y equals a plus bx then you can prove that y bar equals a plus b x bar, all right? And then you can get the value of a, which is y bar minus b x bar. So you can get the value of a as long as you know the value of b. X bar and y bar could be computed by using the original data set. Okay. All right. So we can anyway we can come up with the following result. So this is A, and this is B. What is B? B is the SXY over XXX, and the XXY is the sum of the derivations of XI, YI around the mean value, the center. So you get XI minus X bar times YI minus Y bar. You can rewrite this expression as follows. You get the sum of Xi, YI minus the sum of Xi times the sum of YI over N. And if you replace x by y, you get this one. And if you replace y by x, you get xxx, okay? And if you divide xxy by xxx, you should be able to get the value of b. That's all clear, everybody? It is okay? Okay? Hello? And then you can use what we learned to get the value of a and b in our problem. Can you think about that for a minute? So for our problem, you see that you get the value of x and y, remember? And what are they? In our problem, you get the table, let me see. You get 5, 8, 10, and 2, 5, 7. Then you can find the xy. You can use what you learned, the formula here to get this the sum of the deviations, and that is the 12.6667. You can use the calculators to double check, and the x-axis is the same value, right? Okay, so you can find the value of b, which is the sxy over sxx, and that is 1. You can also find the value of a, which is y bar minus b x bar. B is 1. Y bar is the average value of 5, 2, 5, 7. X bar is the average value of 5, 8, 10. And you get minus 3, I believe. So y equals minus 3 plus x. Do you understand? Is this all right? Is this okay, everybody? Okay. Okay. All right. As I said, I just had another meeting, so I'm afraid that I have to stop the lecture, my lecture today, because I have to attend the graduation ceremony this afternoon. So sorry about that, and I will continue my lecture next Tuesday. All right. Yes. Any questions so far? The quiz. Yeah, yes, that there will be a quiz about the ANOVA. I will make an announcement later today. Okay. The deadline, I will make an announcement on that one. You should be able to check the website for more information. Okay, you will see it. Okay, thank you very much, and see you next time on Tuesday. Okay, and goodbye.